Okay, so we're going to look at tangent planes and normal lines to surfaces. So we're going to briefly talk about the what the theory is in regards to tangent planes, as well as examples to try to um, make it clear whatever that we're going to talk about on the theory section. Okay, when it comes to tangent planes, we have been talking about tangent planes for a long time now. When it comes to functions of independent variables, when it comes to like basic calculus, we have been talking about tangent planes as well as the normal lines. But in this case, if you try to recall under tangent um, under functions of independent variables, we are finding the tangent we are finding the tangent equation of the tangent line. Okay, so what it is now is that you're talking about the equation of the tangent plane, okay, to a surface as well as a normal line. Okay, so in this case, what's the difference is that under multivariable functions, we're not talking about a line. We're not talking about a tangent line. You're talking about a tangent plane. Okay, so it's more like, let's say you have let's say you have this something like that. Let's say you have, let's say, a surface, something like that. So this surface scatters for the this is the z-axis, this is the y-axis, and this is the x-axis. So the plane that is tangent to this surface at a particular point, okay, at a particular point, that is the tangent plane that you're talking about. Let's say maybe it's at somewhere at that point, okay, maybe it's touching somewhere at that point. That's what we are really talking about, and we have the normal line somewhere, something like that. Okay, so the main difference between independent variables and these multi-variable functions, um, we're talking about a plane instead of a line in terms of the tangent, but the normal, it still remains as a line. Okay, so what I would say is that if you have a function, we say let f, okay, let f be a different let f, the function that we have, be differentiable, okay, be differentiable at a point, at a given point, at a certain point, because you're given the equation of the surface as well as the points to try to determine the equation of the tangent planes to that equation at the points that you're given. So that point, we're going to denote it as, let me indicate it as p at y, at x initial, y initial, as well as z initial, like that. Okay, so we have to find that the function that you have has to be differentiable at that point which is on the surface. So we have to keep in mind that that point that we have is on the surface that is given by the equation f x comma y comma 0, like that. Okay, so now we have to say that we are saying we let f be differentiable on the surface at that point. Okay, or let me say at that point which is on the surface. Then that this function that you're talking about is what you're going to write as f of x, y, z, like that. So this is so that you when you try to determine the gradient, okay, the gradient or the normal vector, you would say uh, at that point, okay, this should not be equals to what, should not be equals to 0. Okay, so now we want to try to find out, to say, from this information that we have, okay, from this information that we have right here, what is going to help us to determine the tangent plane as well as the normal line. Okay, so we're going to say the plane through p that is normal to, so the plane that is through this point, okay, um, that is normal to this one here, is called the tangent plane. Okay, I'll say that again. The plane that is through that point, those points that we have, or point P, um, that is normal to what, to what you have here. What that I'm calling, that is more like, this is a method that we use to find the gradient. That's more like the normal vector. Um, that plane that you're going to get is going to be what, is going to be called the tangent plane um, to that function at P. Okay, what about the normal? Or maybe before I go I go to that, the standard equation, let me just, okay, it's fine, let me just call it the standard equation for the standard equation for the tangent plane is we are going to write it as our f. Okay, so try to the equation will really make the statement that I'm just from saying to make a lot of sense. So the equation of the plane is going to be I'll say fx. Okay, uh, that multiplied by x minus o. Okay, then I'll say plus fy. Okay, I'll say fy there, x, y, then we have z there. Okay, at y minus yo plus fz. Okay, so we have x, y, z, z minus z initial there. Okay, so this is what is going to give us the what? This is what is going to give us the equation of the tangent plane. So now I was saying the plane through the point P. Okay, uh, that is normal to what you have here is a tangent plane, and that is simply what we have right here. Okay, so for you to determine this, what this is that when you're given a function, you need to differentiate all that you have in respect to your a, respect to your, I mean, respect to your x, your y, as well as your z. Okay, so meaning if I have, let's say I have a function f x y comma z. Okay, that is equals to xy plus 2x squared plus maybe say z squared, like that. So for me to determine the gradient or the normal vector, I'm going to have my x comma y comma z will be equals to, I'm going to differentiate everything here with respect to what, both like everything with x, y, as well as z. Okay, so this is going to be something like when you differentiate this with respect to x, you're going to have y I here. Okay, y in the I, then that's a product of two functions differentiated with respect to x. Sorry, I differentiated with respect to x, I get a y. Differentiate with respect to y, I get plus what? Uh, I'm going to get plus. What are we going to get? We're going to get x in the j. Okay, plus this we are differentiating with respect to x. How is it going to be? You're going to have 4x in the what? 4x in the I, plus this is going to be 2z in the what, in the k. So you have to arrange those. So it's the same thing whereby you have to determine what your fx is of that function, then you substitute with what the points we substitute with the coordinates that you have for the point that you are given. So this differentiating in this way as well as doing it in this way is one and the same thing. It might appear different, but it's just one and the same thing, like finding the gradient. Of course, someone might not really need or see the necessity to find the gradient. I love the method for using the gradient. Okay, what about the normal line? Okay, what about the normal line now? How do we come up with the equation of the normal line? So the normal line, we say the line through the point P, have the line through this point P. Okay, that is having the direction of this normal vector is called the normal line. Okay, so it is a line that is passing through that point. Okay, that is having the direction of this one. That's what's going to give us the normal line. Then how do we come up with the equation? Okay, how do we come up with the equation? So the equation of the normal line, so we say this is for the tangent plane. This is for the tangent plane here. Then the normal line is going to be something like you're going to have your x, you're going to have your x, which is going to be equals to your initial value of x within that point that you are given, plus your derivative of that function, or let me say your partial derivative of that function with respect to x at those coordinates that you have. Okay, then multiply by what? By t. I believe we are familiar with this. We have done a lot of vector questions. What about our y? Our y is going to be equals to our y initial, okay, plus the partial derivative of y of that function with respect to y at that same point, multiplied by t. What about our z? It's going to be equals to uh, our z initial plus our partial derivative of that function with respect to z at that same point, multiplied by t there. Okay, so uh, this here is going to give us the equation of the normal line, and it's up to us whether we want to put it in parametric, whether we want to use put it in symmetric, or just in terms of like a vector equation. It's really up to us. Okay, so now let's try to look at some few examples. We try to make sense of what we have just talked about right now. Okay, so now let's say we are told we need to find the equation of the tangent line, and then we need to find the equation of the tangent plane and the normal line at the point P. Okay, I'm naming that point as point P. It has the coordinates negative 2 comma 1 comma minus 3. Okay, uh, that is to the ellipsoid that has this equation fx comma y comma z. Okay, that is equals to x to the second divided by 4 plus y to the second plus z to the second divided by 9. So the ellipsoid, the standard equation of the ellipsoid is given in this form: x squared over a squared plus y squared over b squared plus z squared over c squared is equals to 1. This is the standard equation. That's where this equation is coming from. Okay, we'll not really talk about how it looks like, but it's more like you're talking about an ellipse that is in 3D in this case. Like it's scattering for the z-axis, the y-axis. The z-axis both on the negative and the positive. The x-axis, the negative and the positive. The y-axis, the positive and the negative. So it's like you have that kind of like a closed an ellipse that is, it's like a closed. It has like some space inside that is due to its domain. So now first things first, I have to determine what my normal vector is, or I would say the gradient. So this is going to be equals to, if I say that function, okay, f comma y comma z, like that, is to be equals to. So I'm finding the partial derivative of this whole function with respect to x, with respect to y, and with respect to z. Okay, so now differentiating that with respect to x, what are we going to get? The power is going to drop. We're going to have 2x over 4. That will just give us what? That will just end up giving us like you have 2x over 4. You just 2 into 4 is 2. So what you're going to have is you're going to have your x over 2 in what? In the I. Okay, let me write using this color in the I like that. Okay, then we say plus. What about the other part? You're going to have your 2y in the j. Okay, then we say plus. The other one is going to give us 2z over 9 in the k, like that. Okay, so the second thing that I have to do is that I have to determine what really uh, what my normal vector really is at that point. Okay, at the point that I'm given. So it's like you're going to say your f. At what points do we have? We have negative 2 comma 1 comma negative 3. Okay, is equals to. So now it's just a matter of substituting here. So when you put negative 2 here, we're going to have negative 2 divided by positive 2. That will give us negative 1, which is just let me say it's just negative I. Okay, negative I. Then for the other part, we just have to substitute with a 1 on y. We get a 2, so that will give us 2j. Okay, so the other part we have to substitute with negative 3. So we have like 2 multiplied by negative 3 divided by 9. That will give us minus 2 over 3 in the k, like that. Okay, so now keep in mind that we talked about how we arrange the vector, the tangent plane equation. So we're going to start with the x part. Okay, so for the tangent plane uh, tangent plane equation, here's how it's going to be. You're going to have your you're going to have this part. Okay, you're going to have that part, which is your negative 1. The coefficient of what you have there is negative 1. Okay, open bracket. You're going to have your x minus your xo, or your x initial, of which our x initial is what? Is a 2. Negative 2, but because you're subtracting there, you're going to say minus 2. That will become plus 2. and we do that. Okay, then what else? We say plus. Then for this part you get the coefficient, open bracket, you're supposed to say y minus this part. What do we have? You have a 1, like that. So minus here is going to be minus. It was a plus, but because of the minus that I have, I just have to use a minus. That would be 3 over, pardon me, that would be 2 over 3. That would be z minus, what's our z value? It's negative 3, so that become positive 3. So this is the tangent plane equation. Okay, what about the normal? Okay, the normal line, equation of the normal line. So equation of the normal line, I'm going to write it in parametric form, where I'm just going to say it's my x, which is equals to my x initial. Okay, my x initial is our x initial there, plus the partial derivative of that function with respect to x at that point that you are given. And you just repeat the same steps for the y as well as the z. So our x initial in this case is what? Our x initial is what do we have? We have negative 2. Okay, negative 2. Then we are saying plus the derivative, the partial derivative of f with respect to x at that point, which is simply what? A negative 1 there. So that would be minus t. I don't have to say minus 1t. Yeah, what about the y? It will be the initial of y is what? Is 1. Then what do we have? We have positive 2 there. That will give us what? Plus 2t. In the z, what do we have? We have negative 3 as our z initial. Then we're supposed to say plus, but I'll say minus 3 what? Minus is that 2 over 3, 2 over 3t. And this is the equation of the normal line. It's up to you whether you want to put it in symmetric or in parametric. It still means one and the same thing. Okay, and that's how you go about answering that one. Let's try to look at another example. So let's say we are given, we are told that we need to find the equation of the tangent plane at the point P, which is 1 plus pi comma 1 comma 1 there. Okay, for the function f x y z there, which is equals to x minus 4 tan inverse of yz minus z. Okay, how do we determine that one? It's simply one and the same thing. You just have to find what your normal vector is. Okay, so what's going to be our normal vector? So we have the x comma y comma z there. What is that going to be equals to? So differentiating that with respect to x, I'm getting I. Okay, so now when it comes to this part, what it is that I always advise you to say when you're dealing with inverse trig functions, I'm sure there's a lot of methods that you can use. Differentiate your inverse, your tan inverse, which is this part. Then if I'm differentiating with respect to y, I multiply by the derivative of that with respect to y. Okay, because those are partial derivatives. If I'm differentiating with respect to z as a partial, I'm going to differentiate everything here, then I multiply it by the derivative of what you have there as the angle in respect to z. So now when you use there's a triangle. Okay, if you are to take, if let's just say, for example, let's just say this is our function f, which is equals to, I'm going to use tan inverse of yz. Okay, so meaning our yz can also be written as what? As tan f. Okay, so meaning here you need to determine this is just a method that will help us to find the derivative of tan inverse of x, of yz. Okay, so and if you put your angle here to be what? To be f, then you put your yz at this point, then meaning here you have a what? You have a 1 from Sokatewa, because it is opposite over adjacent, making the hypotenuse to be y squared z squared plus 1, like that. So this method is going to help us to come up with the derivative of that inverse. All right, so now when you go through that process, when you differentiate, you're going to find out that the derivative of this part only without the 4, okay, without the 4, so I'm going to say minus 4 like that. I'll say open bracket. So the derivative of this here is simply 1, okay, 1 over uh, y squared z squared plus 1, okay. But in this case I'm going to multiply by the derivative of that with respect to what, with respect to y, of which I'm going to get a what, a z. So in that case we treated z as a constant, okay. So I'm going to say it's plus now. So I'm going to say it's 1 over y squared by z squared plus 1. Then the derivative of that with respect to z, you're going to get what, a y. So minus derivative of that, you get what, you get k. Okay, so here I can't really say this is my j. It's too early for me to conclude because within what I have here, I've differentiated both with respect to y and with respect to z. So I need to try to pair them up, like more like you're trying to correct the like terms. So this is going to be your I, okay. Then I'll say minus 4. So now the thing is that when I differentiated with respect to y, this is what I got, okay. So meaning I'm going to have let me try to simplify this. I'm going to have my 4z, okay, divide by y squared z squared plus 1 in the what, in the j, okay. Then again here you're going to have your minus, going to have your minus open bracket. I'm going to multiply this 4 by the y here, okay. That would be like the 4y divide by y squared z squared plus 1, okay. That would be plus 1. Then that's in what, in the k. Where am I getting the 1 from? I'm just getting that coefficient there. So you find that if we expand this negative by that, you get the 4 by that there. Then the negative, this negative by this positive, you get that negative there, okay. So when it comes to such questions, if you just differentiate that, then you say okay, that is in respect to y, then you indicate it as your j, you're going to be wrong because within the same function you differentiate it both with respect to what, respect to y and respect to z. So it's just a matter of you understanding that that's a product of two functions and you have to pair them up, the z alone, the k alone, sorry, the I alone, the j alone, as well as the k on its own. So now let's try to evaluate at the points that you are given. So the function f at the points 1 comma 1 plus pi comma 1 comma 1, okay. What are we going to get? We see you're going to get our I here, then you're going to get minus. If you substitute with a 1 here, because our z is 1, we put sorry, that's a z, we put a 1 here as well. You're going to have a 4 over 2. Why am I saying 2? You have a 1 here, 1 here. That 1 by 1 is 1 plus 1, that will give us a 2. So what you end up having is a what, sorry, what you end up having is a 2 here, okay. So we're going to have what, a 2j. So what about the last part? The last part here, you have like you're still going to have your okay, you're still going to have a 2 here, then plus the 1 giving us a what, giving us a 3. So that would be minus 3 what, minus 3k. Then what is then, because we already have what we need, we have the point and we have the normal vector, and that will help us to determine the tangent plane equation. So the tangent plane equation, how is it going to be? It's going to be your coefficient here, which is your 1, okay. I don't need to put it. Then you're going to have your x initial. Your x initial is your 1 plus pi. Then you say minus you're going to say minus what, no, in fact it's not supposed to be like this. It's supposed to be your x minus x initial. So our x initial is nothing but what, but 1 plus pi, which I'll just say minus 1 minus what, minus pi, like that, okay. Then I'm supposed to say plus, but I'll say minus 2, which is this coefficient here, okay. Then I'll say y minus the 1 there, okay. So minus the 3 there, which is the coefficient. So you have your z minus the 1, and that is the tangent plane equation. What about the equation of the normal line? Okay, the equation of the normal line will be equals to your x is going to be equals to your x point. I mean, within the point that you have, you get your x coordinate, which is your 1 plus the pi. Okay, then you add it with what? You add it with the coefficient here multiplied by t. Okay, that would be what? That would be 1t, which is just a t. What about your y? Your y is what? Your y is a 1. Then that would be minus what? That would be minus 2t. Why am I getting the 2? It's getting coming from that point and it's a negative. Okay, so the same applies for the z to be equals to what? 1 minus 3t. And that's how you come up with that one. So that is simply how you come up with the tangent plane equations, as well as the normal lines to given surfaces. Once again, this is just we are still doing multivariable functions, where we talk a lot about surfaces, so on and so forth. So that's all in this video. Thank you very much for watching.